TP Group. So it's a name most people haven't heard of. We've been new to the rail market over the last 2 years. We've looked really to bring our knowledge in other markets into the rail sector, and specifically our knowledge around the hydrogen world. So our business has been traditionally set up to work in the defence sector, and we provide hydrogen generation, oxygen generation machines, carbon capture and catalytic treatment devices into things like nuclear submarines, conventional submarines and surface ships. So effectively our business has spent a lot of time creating atmospheres for difficult places. Interestingly, the technology we've got in our business is very similar to the green market and the things that we need as we move forward. And we're a British business. We've been around 64 years, so we've been making money out of making hydrogen machines, and we've been doing that for a long time. And we also provide a through life support service with what we do as well. So we're very much into kind of the holistic approach of front end design, build, test, deliver, support. And I guess the thing for us, kind of sub to rail, if you like, is that in our native defence markets, we're used to 30, 40-year capital lives. Systems have to work. There's no excuses if there's an operational issue, which is similar to rail as well. Safety and reliability is very key. So we need to make sure, because we're dealing with hydrogen and oxygen in electrolyzers, the two mixed is rocket fuel, so it can be a bit dangerous. So we have to deal with that very carefully. And also in our native environments, we've also got things like carbon monoxide, carbon dioxide and NOxes as well. So actually as a business, we're quite used to difficult gases and how you do these things in difficult places. Our transition into the rail market has been focused on hydrogen generation as our area of interest, and that's where I've got a UK factory capability to build electrolyzer machines, and we've also been working with partners to deliver hydrogen fuel cells into one of the UK's first train projects as well. TP Group is an overall business. We're a group PLC, AIM-listed PLC. We are somewhere around 60 million revenues. We're about 450 people now. We operate under 3 verticals. My responsibility is the last vertical, atmosphere management systems, where I've got the manufacturing space in Portsmouth, which has 105 people, probably 70 of which are engineering technical qualifications, others administration support staff. And we principally work on life support systems and are traversing into the clean energy market. We have a consulting business. Consulting business provides feasibility studies. We do a lot of enterprise transformation projects. Most of our work is in defence and aviation. And we've got a rich heritage of managing complex programs for the government. So we'll help decide what's the best technology route to go for new radios, for buying new ships, that kind of stuff. And we'll help set the landscape with the government so the government can actually buy the right assets. And we have a software and digital business, and our software and digital business is effectively providing a range of AI and machine learning technologies. We have a couple of landmark projects, one in oil and gas, and we have one in defence with US government. And what we're doing effectively is we're providing a range of technologies to help people make decisions quicker. We've got a project running in the south coast of England where we're autonomously piloting a boat as well. So we're working with Thales as a subcontractor actually. So it's real kind of proper autonomous technology. Lots of people talk about autonomy and machine learning, but it's not really properly autonomous. The systems we work on are, we pride ourselves very much working on critical programs, things where things go wrong, people get hurt, and also where mission safety is the place to be. It's much more, it's a better place for our business to play than the mass commercial market, which is what we're not set to do. So the atmosphere management system, I think it always, for me, is a graphic. I think someone's actually left Nemo on there, which is always a bit embarrassing. But so just think of a picture of a submarine. So oxygen generator is what's branded as cogs on there. So there's a combined oxygen generation system. So what we do is we take the oxygen from an electrolyzer and we pump that out for people to breathe. We also generate hydrogen in that environment. The hydrogen down there is completely not wanted, and it is a problem gas, so we have to deal with it. And what we do is actually we blend carbon dioxides and hydrogens and other things together to create byproducts which we get rid of. And then we also have catalytic treatment device. So in that traditional environment, you've got waste hydrogen from batteries, because that's one of the things that a lot of people don't think about. Most batteries off gas hydrogen, which you have to deal with, and then you've got other things, carbon monoxides. So if you think of a sealed environment, and there's a couple of TV programs at the moment, Vigil on BBC, which is absolutely not what it's like on board, but it's probably quite nice to see. You've got all the cooking, you've got, you know, people take a link spray on or some of the body spray, all those gases and smells are within that tube and they can't escape. So actually you've got to be able to deal with it, and that's effectively what we do, and clean the air. The principal thing for us is all the systems we produce enable things to stay submerged for 30, 50, 60 days indefinitely, basically until they run out of food. So business model for us is we tend to work in a technical alliance approach. So in our consultancy business, I think I spoke to one of you guys earlier about this, but also in the green energy market, we put together alliance where we work with some key partners to do projects. What we see is that, you know, we're not experts in everything. We're good at what we do and good at what we know, but actually we prefer to work with, you know, partners that come on board with us to help deliver programs. It's a much safer way for our customers and for us to manage the risk, certainly when you start to deal with new projects and new technologies. And kind of re-show the last slide again that I put on my previous presentation. So for us, yeah, our interest really is helping the rail market and the broader rail market look at unlocking technologies, particularly around hydrogen technology. How do you bring safe, reliable systems to market, and how do you make sure that works? And we see that actually, whilst there are other technologies that people produce, batteries and obviously electrification that are critical for our point of view, we've got expertise in hydrogen, so we've got capabilities in safety systems, safety cases, engineering design, product design, testing, validation. So for us, really, that's our key focus point. I think we've done those introductions, so I'll say over to Richard. I think is your slides next. There you go.
Lovely, thanks, John. I'm Richard Kemp-Harper from Arcola Energy. Arcola is a specialist in hydrogen fuel cell technology. We've been going at this for 11 or more years, and actually the leadership team and many of the team have been involved in the technology for much longer than that. Our focus is on applying that technology to give zero-emission vehicles, but focusing on heavy vehicles. That's where I guess the other technologies struggle most. It's where the most obvious market is for the benefits of hydrogen, and where it's where we see it being the best opportunity for a business like us to apply the technology. Over the last number of years, in several vehicle projects, increasing at scale from small lightweight cars all the way through into buses and now into trucks and trains, as I'll talk in a minute, we've matured our technology into a whole platform approach. So we're able to adapt and adjust the various bits of a hydrogen fuel cell powertrain to suit the application. And centered in the middle of the heart of that is our control system, our management of the safety case, the traction, the energy management, the power demands of different vehicles. So what we call our A-Drive platform includes the hydrogen fuel cell tanks, the adaptation of just what the tanks are into safe, compliant, reliable hydrogen systems that you can use to then store your energy on board a vehicle, the integration of the fuel cell into that powertrain to convert the hydrogen into electricity, and think of that hydrogen and fuel cell combination as the energy store on board your vehicle. And then we integrate those with small high power batteries that give you the power. So in a conventional battery electric vehicle, your battery is providing both an energy store and the power delivery for the wheels and regen capture as well. In a hydrogen fuel cell electric vehicle, you separate the energy from the power into the hydrogen and the fuel cell, and the battery is delivering the power. And then we integrate that with the electric motor and all the auxiliaries, control and high voltage electronics to make a complete system. These are our current projects, work on double-deck buses we've been doing for a number of years. The train I'll talk to you a little more about, obviously that's interest here. We're also doing projects with refuse collection vehicles, very similar sort of duty cycle to a bus, very similar environment in terms of running around residential streets, current diesels doing all sorts of emissions and emitting a lot of carbon because there's a lot of energy used, and a fuel cell hydrogen combination is really good for that sorts of vehicle. So onto the train project. This is billed as Scotland's first hydrogen-powered train. It's sponsored by Transport Scotland and St Andrews University, Scottish Enterprise. But the idea is much less about building a train. It's more about building the supply chain in Scotland and industrialising the technology, looking at what the standards approach is to this, to deploying fuel cell and hydrogen technology in the rail sector, and building up the capabilities of potential supply chain partners to understand the technology and see how they could bring components and subsystems into that supply chain. We're going to be having a showcase of the various systems, not the full train, but the systems and how it's built into the train and our approach during COP down at the site where we're working, which is down at Bowness, well, over that side of the country. If you'd like, potentially come and see some of that, talk to me, and maybe we can get you an invitation to some of the days where we're doing that. You can see what we're doing with that. One of the key things about what we're doing, and it's really interesting to see John and tpgroup coming from their sector, bringing expertise from defence and that regulatory environment. We're coming more from the automotive environment and bringing that approach and technologies, approaches to functional safety, approaches to integration and system engineering from automotive, bringing that into rail, but working with key partners who are experienced in the rail environment to translate what we do into the rail context. And I think that we're finding that a really fruitful conversation, and it'd be interesting to see how you're finding the same thing, John, from your perspective. Let's talk a bit about hydrogen trains. We, because of our experience, what we're doing for a number of years, we've got a deep modelling capability that can use this technology and the performance of the subsystems to get under the skin of what's really going on in terms of the power and the energy on board a vehicle. Take a duty cycle, convert that into state of charge of the battery and the fuel cell performance and hydrogen use across the whole cycle. A couple of insights that might be useful from that for you. Again, thinking about the separation of energy and power. In a fuel cell electric powertrain, the battery has been giving you the acceleration, and you get a lot of that back in regen braking. So you look at the train context, trying to pull away from the station, your acceleration, and going up hills, that's delivered by the battery. The fuel cell and the hydrogen is giving you your average energy supply to top up the battery. So think of what the energy demand for a vehicle is. Actually, it's the constant things like the auxiliaries, it's the rolling resistance, it's the air resistance, and that's where your energy from the hydrogen goes. So that's a first order rule of thumb, is to think about those two things, and that is important when I talk about what the capability of hydrogen trains might be. So if I put 25 kilograms of hydrogen in tanks, that's a mass of around 500 kilograms, and that's equivalent to 500 kilowatt hours of batteries weighing 3.5 tons. That's an idea, gives you why you might use hydrogen. You get a lot more energy by weight. You are constrained by volume because the tanks have a certain size. The question then in your range is, how much hydrogen storage can I put on board the train to be able to give me my range? And the interesting thing about that, going back to this point about energy storage, the hydrogen being your rolling resistance and your air resistance, is that doesn't scale with the length of the train. It scales with speed and follow your Davis coefficients, but it doesn't scale with the length of the train, whereas the storage of hydrogen does scale with the length of the train. So the longer trains with hydrogen go further. So a 2-car set we've looked at for that Inverness line, a couple of 100 kilograms, 800 kilometers, we can do what was expected for a day's duty cycle. If you do a 6-car set, and this is some rough calculations, we need to do more work to validate this, but we think we can do 1,500 kilometers or more, and then you're diesel equivalent. So there's a couple of mistakes that I think are made around hydrogen trains in two equal opposite directions. One is that hydrogen trains are irrelevant and can't do anything. I think that's a mistake. I think our evidence, our understanding says that they are relevant, there's a key role. The other mistake is to say that they can do everything and then they'll replace electrification, which is nonsense. Sorry, Secretary of State, but that's not right. But we think hydrogen trains are complementary to electrification. I think this is the map of Scotland. The green lines will never be electrified. They're quite long routes. They've got quite long duty cycles. Those quite suitable for hydrogen technologies. The red ones, let's electrify all of that network. Let's get that done. But maybe there's a role for hydrogen trains in the interim. Let's convert some diesel trains to hydrogen, and let's get the benefits of saving carbon as soon as possible while we roll out that electrification program. So I think diesel trains are quite suitable for a hydrogen technology. That conversion is probably easier than for an EMU, actually. And so we think that let's use that embedded carbon that's already in those trains, convert them to hydrogen. Let's get the benefits of saving carbon as soon as possible while we build out the electrification of the wider network. So I think there's a real complementarity between the program of electrification that we'd like to see and the use of hydrogen trains, and potentially in the other section, the battery trains as well. And where we are with that, just finally then, we've got a packaging study underway for a proposed first train that might go into pilot service. I don't know if Frank is there from Hightrans, looking at the far north line, seeing if we can put that into service there, and also with other partners exploring what that route to pilot service is and what the first fleet might look like. To move from let's stop doing demonstrators, we really need to understand what's going on at the fleet level and how this is really deployed in operations in a depot, and the practicalities of getting this technology into the real world. So I think that's all for me. Thank you very much, and look forward to your questions.
Kevin next, please.
Thank you. So I'm Kevin Fothergill, and I'm part of an organisation called EnAcumen, and we are consulting specialists in the field of hydrogen fuel cells. I've worked in hydrogen since 2004, and my colleague Peter Gray on the slide there, he's worked since about 2002. So we've got a lot of fairly deep understanding of the history of hydrogen, how it's developed, what challenges it's overcome, and those range from technological challenges, adoption challenges, financial and economic challenges, and we've seen all the people who play in the market. The job that I had was as commercial director for Johnson Matthey Fuel Cells, and we were basically visiting all of the fuel cell manufacturers in the world and all of the electrolyzer producers in the world to sell them components. So we have a very good understanding of the technologies that these people have, their applicability in different situations, their strengths and weaknesses, and their business models, I guess, as well, how they approach business and how they want to sell. So this knowledge, I guess, we use to help organizations, companies to quickly learn about hydrogen, quickly learn about what is an option and what isn't an option, who to talk to, what the key questions are, and help them to get to those answers as quickly as possible, because it is a complicated subject, and you can spend a lot of time trying to learn it from scratch, and we're there to help bring that along. So that's us there. The thing that I want to talk to you about now is not so much the product offer, but to give you an example of some of the work that we've done, which is around addressing some of the challenges that prevent hydrogen from becoming commercialized. And if I go to the next slide, how do I do that? Is it just
the arrow key on the keyboard?
The arrow key on the keyboard? No, wrong. I would get it wrong. There are 4 arrow keys. So green hydrogen. You can make green hydrogen by electrolysis if you've got green electricity, and in some places it is very cheap to make because the electricity is very cheap, and the electricity component of hydrogen is really by far and away the biggest element. Depending on what you're doing, maybe 80% of the cost of the hydrogen you produce. So the cost of green hydrogen is very, very sensitive to the electricity cost. In some locations, you can produce hydrogen very cheaply. And the chart there on the left shows the cost of hydrogen in dollars per kilo. Sorry, it's in dollars. I stole this from the International Energy Agency. It's dollars per kilo of production. And if you look along the two lines there, they're going on the x-axis is about hours of operation of these electrolyzers. So one of the key things about renewable energy, of course, is that it tends to be intermittent. The wind doesn't blow all the time, the sun doesn't shine all the time. So in those areas where you can get very high load hours and minimize the effect of intermittency, you can get much, much lower costs of production. So the green line there shows you if you have $30 a megawatt hour for your electricity cost, which is probably about a third of what we could realistically achieve here in the UK. So, you know, that just shows that there are some locations where you can get very, very low cost hydrogen. This example is the Middle East, actually. It's an example of combined wind and power in the Middle East. And if you can make your hydrogen that cheap, then you've started to address one of the fundamental problems, is that hydrogen is going to be more expensive than diesel. You know, and if I'm going to change my technology, I'd rather it didn't cost me too much more. I want to do the right thing, but you know, there's a limit to what I'll pay. And so if you can keep the costs down, then that really helps with doing this. Now, the problem is that this very cheap hydrogen, of course, is miles away from where we really want it to be. So if we're trying to consume here in the UK hydrogen, we can either make it by electrolysis here, and there's a certain cost to that, or we can bring it in from, for example, the Far East or the Middle East, should I say the Middle East. The problem with bringing it in from the Middle East is hydrogen is very, very expensive to transport. And in fact, even within the UK, if you were to make hydrogen, let's say at Grangemouth here in Scotland, and transport it more than about 100 miles, you're probably going to double the cost of that hydrogen. So you then suffer from, you can't produce hydrogen at a very large scale and ship it around the country even. You know, so you have to make it in small scale. Small scale inherently means relatively high costs. So what we are looking at here, if you look on the right-hand side there, you can see a chart which shows you how much compressed hydrogen gas you can get into a 40-ton truck. And it's that one less than 500 kilos. So that's a 40-ton truck, and you can get less than half a ton of hydrogen on it. Because the hydrogen is very low density, and because you have to have very, very strong steel cylinders, very heavy steel cylinders in which to keep it, because you've got to put it under high pressure. If you look at the next line across, it's liquid hydrogen, and liquid hydrogen you can transport more of. It's very expensive to produce, unfortunately, and the capital cost is very high to do that. And then the final one is ammonia. So what I'm saying is ammonia provides a means of bringing hydrogen into a sensible realm of transport cost. So liquid ammonia contains more hydrogen per cubic meter than liquid hydrogen does. And it can be transported very cheaply, and already is transported very cheaply. And this is the final slide, just to give you an example of this. We've done a couple of studies. We've actually done a study for, we've done 2 studies for rail, supply of hydrogen to rail using ammonia as a means of getting the hydrogen to the depot. And this is some of the results of that. First of all, ammonia is easily produced. It's very cheap to produce. It's produced in huge quantities, 180 million tons a year. It's been made for 100 years. This is a mature, low-cost, high-efficiency process. You can then transport it. And if you look at the right-hand chart, the top there, that shows you the cost of transporting bulk ammonia from the Middle East to the UK in dollars per kilogram of hydrogen delivered, assuming that you've then delivered the hydrogen 100 miles by road once it arrives in the UK. So you're adding about, in this case, what, under 35 cents. So about 25, 30 pence a kilo. So quite a small proportion. And then the chart in the middle there just adds up all the costs that you have in comparison. So the left-hand bar shows if you were to make hydrogen in the UK using UK electricity costs, and you were to transport it 100 miles to the end user. And the bar on the right in that chart shows if you did the same thing, but you'd made the hydrogen in the Middle East and transported it over. The diagram below just gives you a schematic of how you do that. And the key things here are very high load factor, very big electrolyzers. You're going to make 180,000 tons a year of hydrogen. You're going to put it into a 1 million ton per year plant to make ammonia. That's entirely typical of ammonia plants. You're going to put it onto a big ship, bring it to the UK and ship it out. And in many cases, you could probably do that cheaper than if you were to make the hydrogen in the UK. So I just want to say that there are other options about how you get the hydrogen to your end user. And this is an example of the kind of work that EnAcumen does to try and help people solve some of these problems of supply. That's it.
Thanks, Kevin.
Thank you.
So, thank you very much for the talks, guys, because it ties really nicely into what my position is here at H2 Green. So I'm the managing director of H2 Green. We're a wholly owned subsidiary of the GTEC Group, which is an AIM-listed business. Myself and GTEC have a long energy industry history, mainly in the petrochemical side. For myself, I've spent 20 odd years making the problem as a petroleum geologist. And so paying for my sins at the moment. But we come into this role as the developer of a hydrogen production, dispensing and retail project development company. And what I want to try to address today, I think, is really a little bit bigger picture than individual trains, actually how the rail system has an opportunity to influence a hydrogen economy and you know, be much above its own, over its own footprint, and how it actually is part of a greater solution. So a little bit of background for us. We are building a hydrogen network around the country. We're focused at the moment on the UK, but we've just opened up an office in The Hague. Our sweet spot for us are production facilities of around 8 to 20 tonnes per day production. On site in a centralised hub that would then service the transport sector predominantly. But we have 21 sites at the moment around the UK that are at various stages of project development, none of which are operational yet. But we'll be producing that hydrogen essentially adjacent to where the customer demand is. And in the coming weeks, I'll be able to talk a little bit more about one of those, which is also on a rail site. And has the option here to provide hydrogen directly to that rail system, as well as servicing the HGV market. We've got an ambition here to put a hub in every major population centre in the UK. And I just want to point out that the interesting thing is that it's not a problem for me to raise that capital to do that. And it's nothing bold or beyond remit to say that we could go out and build that level of infrastructure. That capital is banging on my door on a daily basis. The thing that we require is an agreement on offtake. If I can have an offtake agreement, then I can build that site tomorrow. Well, at least John will build it for me in 18 months from tomorrow. So we're looking here at leveraging hydrogen as a vector that helps, decarbonise transportation, but it also has important byproducts. Things that John has been using in the subs for a long time. That oxygen can be used to accelerate aerobic digestion in sewage treatment plants. It can be used in medical purposes. It can be used to try to reduce some of the mortality in the aquaculture. That's all part of a benefit that is intangible to the rail system, but relevant to developing a national hydrogen network, as well as producing low-grade heat. In this site that we're soon to talk about, one of the opportunities that we're pursuing is providing that waste heat as a product to the railhead to provide that to the station. And I think Kevin really summed it up very nicely. We think the core requirement for a hydrogen development system is to cut transportation out of the equation. I think the concept of saying that we need to have one or two really large hub and spoke type hydrogen developments inside the UK and then store them in salt caverns and ship them around the country misses the point that Kevin raised earlier. Transportation of hydrogen is painful at best and certainly extremely expensive. But why would we base a future network on the premise of how we used to run oil and gas? As a geologist, my job was to go and find the stuff wherever it was in the world and then help develop the facilities to pull it out of the ground, transport it to a refinery and get it converted into a product that you want to use. And it was a great product, let's be honest. Diesel's a fantastic fuel, except it kills the planet. And so, that's why we're talking about changing it. But it comes at a cost. We are weaning ourselves off a very effective fuel source onto something that is less optimal. So we have to find that the benefits in all of it, all of the elements of that supply chain as we can. And one of them is wherever you have water and electricity, we can create the hydrogen for you. And so one of our focuses is to produce that hydrogen near where the customer needs it at scale, and leveraging our oil industry background, we produce that using multiple trains, forgive the different use of the term there, but multiple trains of production to increase redundancy, just like we do in offshore production. The weak point is not the electrolyzer, it is the compressor system. We need to be able to run them low and slow, keep varying that, but as long as they're turning constantly to avoid that static friction and increase that reliability. And we do that, we design it around that premise, because the moment we don't deliver hydrogen to a train or a bus is the end of it for us. So security in supply is essentially becoming our brand. We talked a bit about cost, and I just wanted to give you a little bit of data on this, a little bit of history on what's going on. So if you haven't paid attention to the news recently, you probably paid attention to your gas bills, and if your company's disappeared, that was your supplier. Let me give you some context for that. In essence, the price crush that we're under at the moment in both gas and electricity is simply linked to the fact that we had a cold winter last year. We've had a year of seasonally low winds, and our backfill for energy to the UK is no longer coal, and we're turning down the nukes. So we rely upon gas. Now, the UK continental shelf gas and the Norwegian gas is fully contracted. So our last place to go is the Russian gas pipeline. And I don't believe the conspiracy theories that Putin's squeezing the taps on us. The reality is that they've had postponed maintenance due to COVID, and that's now coming through. And they just can no longer safely operate those lines without those maintenance, so we'll be able to restrict that supply. And that's driven gas prices through the roof. But that period of low wind has then tied electricity to that market, and they mirror each other exactly. And the reason for that is this is our dispatchable power that we have in the UK at the moment. Of course, when it hit 200 pounds per megawatt hour, we turned on the interconnector, or we turned it up rather, with France, and it caught fire. That was us accessing the nukes in France. So that was our access to the non-dispatchable, to the dispatchable power that we were missing at the moment. So this is a major problem, and this is certain economics, socioeconomics that are happening at the moment that have caused this. But this is the future of our energy system, and understanding how any solution that we approach is part of that whole solution, the whole energy chain, is critical to making national scale investment decisions. We have always built our energy demand, our energy consumption, on the concept that if I turn on the power switch, electricity will be provided to me. That's a demand side response. You can turn up the gas, you can turn up the coal, and you get more electricity. We behave very similarly. We have peaks in the morning when we get up and boil our coffee and tea, and we have peaks in the biggest peak later on in the day as we head home, turn on the oven and start watching television. Very predictable. They even include things like the end of TV shows or football games in that prediction. But that's not going to be the truth in the future. We're going to move towards more of a position where we have a greater component of non-dispatchable power. Storage as a solution doesn't yet exist, and arguably the economics will always remain challenging. So what we need to have is a supply-led energy consumer. We need energy consumers that understand they need to be able to take advantage of low-cost power that occurs at off-peak times. And that's where I see hydrogen in the rail system is actually offering an additional benefit that I don't hear spoken about very often. And that is that the rail system, as a large demand user for electricity, by taking more of that electricity from a source that's stored, gives you the option that becomes part of the greater solution. And interestingly, the journey towards overhead electrification and adding in more trains at peak hour times when we already have peak load on the electrical system is an impact on the national grid and the infrastructure for energy generation that I don't think is being talked about. And we're talking here about rail, thinking that this is a beautiful, unique butterfly, but it sits within an ecosystem and that ecosystem has to connect. And that's where we see a story that needs to develop as coming together as part of a holistic solution. So we do agree that any kind of overhead electrification system for rail is obviously the cheapest. It's the cheapest to buy, the cheapest to operate, the cheapest to maintain. But it doesn't help us with that energy time shifting against that demand. And what we're trying to get the government to understand, and we're working heavily with BEIS on this, is to get them to realise that these trains and the hydrogen systems that can feed them become large virtual power plants that can respond to those demands. We operate our systems between 30 and 80% of its load factor. The more electricity I pump through my electrolyzers, the more resistance the electrons offer. So the more energy I consume per kilogram of hydrogen. So the best operational efficiency, and Kevin's right, about 80% of my cost in hydrogen is not the capex, it's the electricity. So I'll buy more electrolyzers and run them at 30% capacity because I'll run them cheaper. And I've got no problem in raising that capital. But I'll run it at 30%, not zero. I don't care to turn off and on because I don't want to ruin my compressors. Run it at that 30% during the peak hours, and then at night turn that up to 80%, maybe 100%. If we're digitally connected with those day ahead forecasts and energy demand, I might run more hours at 30% and fewer hours at 100% to help balance that system. And the national rail system can be part of that solution. And that's something I'd love to hear in the discourse coming out of events like this. What can we do beyond just servicing, decarbonising what, quite frankly, is not a very significant carbon footprint? It's great how efficient rail is. And yes, we can get more people off roads onto rail. That's one way of addressing the problem. But decarbonising diesel trains doesn't impact the carbon footprint of the UK as significantly as it could be as part of a greater solution. So we're hoping to influence that government discussion and to get it into the position where they recognise this is a major lever that can stimulate the hydrogen economy. Large offtake, if you can give me a contract for large offtake and long-term offtake that you can have with rail demand, we're able to then unlock that capital and get those systems deployed. And you know that I will build them in a position where I've got surplus capacity. That makes it easier for other consumers to develop in alignment with that, with the heavy goods and the light goods vehicles and the consumer vehicles in the long run. And so fundamentally for me, I think part of this story, and I think we can champion that as a group of interested parties in the rail sector, is bring the conversation back into how is this part of the total solution and not just a replacement of fuel for a train. Thank you.